And then a short one now on the distribution function, because we are almost there. Let me say the words and then let's do the general comments afterwards. The distribution function is, in a way, it's kind of an alternative to the density, and you can find the distribution function from the density or even define it from the density like this, because by definition, the distribution function is the probability of being less than or equal to x. That's the definition of the probability function, the distribution function, sorry, CDF. Sometimes the cumulative density function, if you want. It's a bit of maybe confusion about the naming and abbreviation there. And here's the mathematical way to put it. Actually, the principle you might already have used at my last question from before almost, to where I asked about what's the probability of being less than 3. That would be the same as saying the probability of, probability of being less than 3 would actually be the same as the probability of being less than or equal to 2, right? Which would then be the distribution function evaluated in 2, if we want to make the connection. Now that we have defined the distribution function. Yeah, here it is again, where we basically see the thought here. It was applied to the fair dice example, not the unfair dice example. So distribution functions and density functions are two ways of specifying all the probabilities that goes with a random system, to be very general in the saying, right? If the random system or the random phenomenon is given by one throw with a dice, that's a random system, a simple one. To be in control of a random system, you must know the probabilities. And that's the concept of randomness. You don't know what's going to happen, so you cannot be in control by knowing what's going to happen. But you can be on top of the system by knowing all the probabilities. That's probability modeling, right? So if you know a system and you know its probabilities, all of the possible ones that could be there, then you're on top of the world. So we need a mathematical construct or concept to collect all the relevant probabilities in some construct and with some name. Well, here it is, the density function. That gives all the individual probabilities. That's one collection of probabilities that would tell the full story. The distribution function is another, because you can go from one to the other, right? If you have the densities, you could find the probability distribution function. And if you have the distribution function, you could actually find the density by suitable subtractions of the distribution function. So there are two alternatives to tell the story about all the probabilities. For many reasons, it's good to be able to have both of them there in our way of dealing with probabilities. Sometimes it's the pointwise probabilities we need to work with, and other times it's those accumulated probabilities we need to work with. Both have their place. And a little technical thing, what if we had a probability challenge like this? Well, that's not the distribution function. If I want the probability to be 3 or above, we can make this complementary probability. Again, I use those basic rules without any statement of the rules. I assume we can all remember those basic rules. Such that that would be the same as taking 1 minus the probability of being less than or equal to 2, right? Because I have the complementary thing. So either I'm above 3 or I'm 2 or above. Below, those two add up to 1 because that's everything. So I can jump between them. So I could also get this one from the distribution function like this. That was the distribution function.